Welcome back to AI Paper Podcasts. Today we're diving into a paper that really challenges a core assumption in how we build generative models.
Right. For years, the thinking was if you want to use one of these huge pre-trained encoders, you basically need an equally massive and complex generator to handle it.
And this paper says, maybe not. We're looking at one layer is enough, adapting pre-trained visual encoders for image generation.
And the title really gives the game away. They tackle this fundamental problem. You have these incredible visual encoders like DINOv2 or SigLIP that use super high-dimensional features. We're talking 1536 dimensions because they're built for deep understanding.
But then you have generative models, like diffusion models or normalizing flows, and they need stability. They thrive on these really compact, low-dimensional latent spaces, maybe just 32 dimensions.
It's a massive mismatch. And the solution they propose, the feature Auto-Encoder, or FAE, is just so simple, it's brilliant. It basically compresses all that rich high-dimensional knowledge into a tiny generation-friendly code.
Using, and this is the kicker, as little as a single attention layer as its encoder.
And it works. On ImageNet 256 by 256, FAE gets a state-of-the-art FID of 1.48. But the crazy part is the speed. It hits a really competitive FID of 2.08 in just 80 epochs.
That is an incredible acceleration. It shows you can reuse all that pre-trained power without inheriting all the complexity. So let's unpack this.
Yeah, let's get into how they actually solve this dimensionality problem.
Okay, so let's break down this core conflict. We've seen huge progress in visual generation, mostly because people figured out how to plug in these big self-supervised models.
Yeah.
Why has actually getting them to work together been so difficult?
Well, it really comes down to what the two systems are designed to do. A model for understanding, like one of these big vision transformers trained on mask image prediction.
Right, where you hide a patch of an image and ask the model to guess what's there.
Exactly. For that task, you need a high-dimensional space. If you mask out a piece of a dog, there are so many plausible things that could be there, a collar, maybe the background grass. That 1536 dimensional space is needed to model that whole complex distribution of possibilities.
So the high dimensionality is for flexibility, for modeling uncertainty.
Precisely. But then you hand that massive embedding over to a generative model, especially something iterative like a diffusion model, and the whole system becomes incredibly sensitive.
Sense of how?
In a diffusion process, you're constantly calculating gradients to denoise the image step by step. In a high-dimensional space, the math gets really expensive, sure, but more importantly, the whole denoising trajectory becomes unstable.
You mean small errors get amplified?
That's it, exactly. These high-D spaces can lead to vanishing or exploding gradients if everything isn't perfectly tuned. The whole process becomes unstable, and convergence just slows to a crawl. That's why generators prefer these cozy little 4 to 64 dimensional spaces where everything is smooth and predictable.
So FAE's big insight is basically questioning if we even need that high-dimensional complexity for the generation task itself.
Exactly. Their argument is, look, the original encoder needed all those dimensions to handle masked inputs, but our adaptation task generating a clean image only ever sees unmasked inputs.
So the need to model that diverse set of possibilities just disappears.
It's a whole different ballgame. The goal isn't to preserve the exact high-dimensional structure anymore. It's just to leverage the rich semantic meaning that's inside it.
And this really explains why the old solutions were so clunky.
Totally. You had methods like VA-VAE, which were these complex feature alignment models. They used extra objective functions and multiple training stages to try and force the big space into a small one, but you always lost information along the way.
Or you had the opposite, like RAE, which just tried to use the full 1536 dimensions directly.
Right, and that meant you had to completely redesign your generator, making it wider and more complex just to handle the huge input. FAE just sidesteps that whole debate.
So let's get into the architecture, because this is where the simple yet effective mantra really shines.
This is the coolest part. The core of it is the single attention encoder. It takes the patch embeddings, which might be, say, 16 by 16 by 1536 dimensions.
And it squishes that down to 16 by 16 by 32?
It does. And it does it using just one self-attention layer followed by a linear projection. That's it.
Wait, hold on. One layer. To go from over 1,500 dimensions down to 32? That sounds like you'd be throwing away almost everything. How does any of the important information survive that?
That's the genius of it. They're using simplicity as a form of regularization. See, the task of reconstructing the features is way easier than the original pre-training task the giant encoder was built for.
Okay.
So if you use a deep, powerful encoder for this adaptation step, it has so much capacity that it'll just overfit. It might learn to completely re-encode the features, throwing away all that valuable pre-trained knowledge you wanted in the first place.
So by keeping the encoder incredibly shallow, just one layer you're forcing it to be.
Whoa.
Hey, lazy. It can't learn some complex new transformation. It's forced to just find the most efficient way to pass along the most important bits of information.
Exactly right. Simplicity ensures fidelity to the original semantics. And it's crucial that it's a self-attention layer, not just a linear one. A linear layer would act on each patch independently. The self-attention layer looks across all the patches and can identify and remove redundant global information like, say, the overall lighting of the scene that's shared everywhere.
Which makes the final compression of the unique, patch-specific details much more meaningful.
Precisely. And the ablation studies they run later completely back this up. The single attention layer beats both a purely linear layer and, counterintuitively, a much deeper 6-layer transformer. Simplicity literally wins.
Okay, so you have this tiny, well-behaved latent code, Z. What happens next? This is where the double decoder design comes in, right?
Yep. They separate the problem into 2 stages. First, you have the feature decoder. Its only job is to take that tiny latent Z and map it back to the original high-dimensional space, creating a reconstruction called X-hat.
So it's trying to undo the compression?
It is. It's a 6-layer transformer, and it's trained with a really simple VAE objective, just an L2 distance. How close is our reconstructed feature X-hat to the original feature X plus, a standard KL term to keep the latent space regularized?
And I see they use modern components here, like ROBE and RMS norm. Why is that important at this stage?
It's all about stability and quality. They found that high-quality feature reconstruction is the best predictor of good downstream generation. ROBE helps maintain the spatial relationships between patches, RMS norm is more stable for training deep transformers than layer norm, and SWIGLU helps information flow better. It's about making this first reconstruction as perfect as possible.
So once you have this high-fidelity reconstructed feature map, X-hat, that's what you use to actually make the image.
Yes. The second decoder, the pixel decoder, takes that reconstructed feature map X-hat naught, the tiny latent Z, and turns it into the final RGB image. This is a brilliant move because it decouples the hardest part, pixel generation, from the compact latent space. The feature decoder has already restored all the rich semantic context for it.
And they have a clever 2-stage training process for that pixel decoder, too.
They do. In stage IB, they actually inject noise into the original frozen embeddings to make the decoder robust to small perturbations. Then in stage 2, they fine-tune it on the actual clean X-hat reconstructions coming from their own FAE. It guarantees the final result is both robust and high fidelity.
The whole thing is just so modular. Because Z is so small and stable, it really can act as a kind of universal plugin for any generator.
And they prove it. They hook FAE up to 2 totally different types of generative models. They use it with diffusion models, CT and lightning DIT, and they also use it with a normalizing flow model called StarFlow.
And the integration was just simple.
Seamless. They just replaced the model's original latent representation with their Z. No extra alignment losses, no re-architecting the generator. It just worked.
Which brings us back to that crucial question. Did the semantic information actually survive that aggressive compression?
It's honestly astonishing how well it did. The paper has some great visualizations. First, they look at within-image similarity. They show that patches that are semantically related in the original DINOv2 space-like to parts of a cat's face are still just as related in the FAE latent space. The internal geometry of the object is perfectly preserved.
But the cross-image examples are even more convincing.
Oh, absolutely. They show that you can take the latent representation for the eye of one cat in one image, and using just cosine similarity, find the eye of a totally different cat in a completely different image.
That's incredible. It means the model has preserved these fine-grained, part-level concepts. That's exactly the kind of nuance you'd expect a single-layer encoder to just completely destroy.
Right. If you can reliably map the abstract concept of cat eye across different instances using just 32 dimensions, your compression has done its job perfectly.
Okay, let's talk numbers. Let's look at the benchmarks, because the efficiency argument really has to be backed up by performance.
It really is. On ImageNet 256 by 256, the speed is the first thing that jumps out. It achieves a really strong FID of 2.08 in only 80 training epochs, and that's without any classifier guidance.
For anyone who trains these models, getting that level of quality that fast tells you the latent space you're working with is incredibly clean and easy to learn from.
And it's not a trade-off. They don't sacrifice peak quality for that speed. If they let it run for 800 epochs, FAE gets a state-of-the-art FID of 1.48 without guidance and NearSOTA 1.29 with it. It's a clear improvement over previous methods like VA-VAE.
And what about generalizing to other tasks, like text-to-image?
Equally impressive. They train on CC12M, which is a fairly small data set these days, and still got FIDs down to 6.90 on MSDSO.
And the charts in the paper show the convergence curve is just dramatically better than baselines like SDVAE. FAE starts from a much better place and gets to good results with way less training.
They even validated it with the star flow model, the normalizing flow. The FAE version got an FID of 2.67, way better than the baseline's 4.51. It just proves that Z is a better, more general-purpose starting point for generation.
And all this while, the latents are still useful for understanding tasks, right? They didn't break the original encoder's purpose.
Not at all. The reconstructed features still get 86.17% top-one accuracy on ImageNet linear probing. The semantic integrity is still there.
Let's quickly touch on the ablation studies, because for a technical audience, this is where they really prove their architectural choices. It's not just that one layer is enough.
It's that more layers are actively worse. That's the key takeaway. The single attention layer got a better final FID score than a deeper 6-layer transformer. It proves their theory that a shallow encoder is a necessary constraint to stop the model from overfitting the easier reconstruction task.
And what about the choice of 32 dimensions? Was that the magic number?
It seems to be the sweet spot for generation. They found that if you went up to 48 or 64 dimensions, you got slightly better feature reconstruction. X hat was a tiny bit closer to X, but the final FID, the image quality, was actually best at 32 dimensions.
So the generator benefited more from the stability of a super compact space than it did from that marginal gain in reconstruction fidelity.
That's it. It's an empirical validation that for generation, compactness is king.
And we should also mention that they used some modern tricks in the generator itself, like the timeshift parameter in the diffusion process, which also helped with the rapid convergence.
Absolutely. The FAE framework is one part of the solution, but they paired it with a highly optimized generator architecture to achieve those SOTA speeds. It's a full system.
So to recap, it's a minimal encoder that creates a perfect latent interface, a robust double decoder, and an optimized generative model. It's a masterclass in balancing simplicity and performance.
It really is. Now, there is one trade-off they're very upfront about. Because the FAE encoder isn't trained for direct pixel reconstruction, metrics like RFID, which measures that, are not as good as models designed specifically for that.
Right. FAE gets an RFID of 0.68, while a model like VA-VAE gets 0.28. But VA-VAE is much slower to train for generation.
It's a deliberate choice. They prioritized final generative quality and speed over perfect pixel-level reconstruction.
And that choice leads to a really fascinating final thought. FAE shows that a tiny, single-layer adapter can capture the semantic core of a massive pre-trained model. If 32 dimensions is enough to hold the generative essence of DINOv2.
What does that say about the true intrinsic dimensionality of semantic information?
Exactly. If we could compress out 98% of the feature dimensions with just one layer and lose almost nothing of value for generation, how much of what we were modeling before was just redundant? It makes you wonder what the next step in architectural simplification might be.